Okay, so this video is to support your reading in section 8.2.2. And we left off with this slide and talked about how our delta G value, which is something we could measure, is really telling us something about the difference in chemical potentials between reactants and products. Okay, so we're going to take that now a little bit further to see how that works. We can generalize our previous statement to say that delta G is going to be equal to the sum of all the chemical potentials of the products minus the sum of all the chemical potentials of the reactants. And if in equilibrium, that should be equal to 0. Okay? Because nothing's changing. Delta G shouldn't change anymore. Our free energy doesn't change. We reach equilibrium. Okay? It means if it's not in equilibrium, then this should get smaller. Delta G should get smaller in spontaneous interactions, which we can see what matters here. So let's use for an example the formation of water. Okay? So that takes two molecules of molecular hydrogen, which is diatomic, plus one molecule of molecular oxygen, also diatomic, into two molecules of water. Okay? So our reactants are these two, and our product is this one. So in equilibrium, that should be equal to 0. And so we have double 2 factors, okay, of the chemical potential of this product minus 2 factors of the chemical potential of this reactant minus 1 factor of the chemical potential of this reactant. Now remembering how chemical potential is defined, okay, you can look back at previous videos, okay, but what we had is we have KBT times the natural log of the ratio of the concentration over some reference concentration. Okay, and again, this reference concentration is often chosen to be 1. All right, now the factor of 2 comes in front of the natural log, and then I'd have to repeat that natural log for the different concentrations. But then each one of these chemical potentials also had a term that is dependent solely on temperature, okay, constant otherwise. Okay, and so we have these, well, I should say dependent on temperature, and it depends on the parts of the molecule, like its internal energy and its mass. Okay, but we have 2 factors of that, minus 2 factors of that, minus 1 factor of that. So please, again, if this is confusing, I want you to go back and look at our definition of chemical potential and see how this line becomes these 2 lines. Okay, with that, we need to do a little bit of algebra. And we're going to set that to 0 and do some of our powers of logs. And so a factor in front of the natural log becomes a power on the argument of the natural log. And if we have natural log of A plus the natural log of B plus the natural log of C, same thing as natural log of A times B times C. So I've taken this whole thing here and thrown the factors on top of the arguments, including that minus sign. Minus 1 goes up here. And then I've combined them all to be able to create this. Okay? And then I've just carried over that second term. Okay, this term right here. Okay, so now this is all equal to 0. So let's subtract this to the other side, divide by KBT, and then exponentiate both sides. Okay, well, we had this divided by KPT, and we exponentiated it. Remember, we subtracted to the other side. That's why that's minus. And then if we take the exponentiate and natural log, it just brings down whatever's left. Now, if we look at that, that's going to be C of the height of the water squared, divided by, because of the negative 2, C of the hydrogen squared, divided by, because of the negative 1, C of the oxygen squared. And now there's 2 factors of this constant in the denominator, 2 factors of this constant in the denominator of a denominator. Those cancel. And I'm left with 1 factor of this constant in the denominator of a denominator, which throws it into a numerator on this side, which I'll divide down onto this side. Again, if that was a lot of math, please take pause the video and go try and do that math, write it out, so you can see that that worked out. That's going to help you more than just watching me do this. Okay. All right, so now we have this ratio of concentrations raised to the power at which they appear in the chemical reaction. Okay, this stuff all over here is dependent solely on the mass of the particle, the internal energy of the particle, and other constants that are functions of temperature, or other things in a factor of temperature. And then we have the thermal energy. So all of this stuff here we call K equilibrium for the reaction, and it's something that you can measure. Okay, in fact, we'll see just in a second. And we usually just disregard this C0 because we usually use it, again, as 1 molar. So we reference everything in terms of molarity, or 1 molar. So this was our example for water, the formation of water. But this leads, the same process leads to what we call the mass action rule. And that's for any chemical reaction. And if you look at this, and use the notation talked about in the book, where these brackets describe the relative concentration, relative to 1 molar. Okay? And so we get this, and so this would be one product, so product 1, raised to its value it appears. That's what this variable nu, this is the variable nu, Greek letter nu. That would be the number it appears in its chemical equation. Okay, so 2H2O, we have a 2 there. And do that with all the products. And divide it by the same thing for all the reactants. And those should always equal KQ, which we've shown before that all of these things can be equal to what we call the Gibbs free energy for those constants. Okay, this looks a lot like the Gibbs free energy we saw before, but it's the constant part of it, or the part that's dependent on not on concentration, just on characteristics of the molecules and temperature. And that's something that can be tabulated. You can just do some experiments and tabulate that. So this whole constant of this equation can be looked up and tabulated for different temperatures. Okay, so that's the mass action rule, and it's basically a ratio of the concentrations. And you'll be able to use this with one of the homework problems.